You're listening to Würth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Würth Electronic technical specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, PCB heat management today, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Electronics What's Up podcast. Thermal management has been a very big and trendy topic in the industry lately. Now, when we're talking about designing and arranging electronics in this industry, doing something effortlessly is almost unheard of, since there are so many details that need to be taken into consideration. Well, today we're combining the topic of decreasing the temperature on your PCB and doing so effortlessly. And this podcast will guide you through the art of designing traces based on two key IPC standards, while applying them through concrete examples and tests. We'll do so by altering temperature rise with the same traces, same connectors, and current, but with different configurations. We'll tackle all these tips and tricks, and at the end of the presentation, you'll know how to better cool your PCB.
The agenda for today will talk about temperature, which is always a big topic for PCBs and for, in general, electricity. So we'll see consequence of temperature. I will just change this is better. The consequence of temperature on the PCB. We'll talk a little bit about standards and how to design your trace. Don't worry, that will last a couple of minutes only. Standards are not always so funny to talk about. And after that, we will be able to see some example on how to improve and cool down your PCB quite easily, to see some tips that maybe you don't know. And we'll see if it's possible also to cool down the LEDs on the PCB. So now, consequence of high temperature. First, a little bit of vocabulary. Connector for power is, let's say, could be just considered as a resistor, such as a trace. That's, of course, different for data traces, but we are talking about power. So this is a resistor with an ambient temperature T. This is usually given in degrees Celsius. And if you put current in a resistor, all of you knows that because of the Joule's effect, then it will release heat in the air, well, generally in the environment. And so the temperature will increase. That's called temperature rise, and we call that usually delta T, and that's mainly given in Kelvin instead of degrees Celsius, just to make a difference between delta T, temperature rise, and ambient temperature. Okay, now, what is the consequence of high temperature? This is a curve that is given by the Swedish scientist Arrhenius. This is the Arrhenius equation. You've got the temperature in the x-axis, and in the y-axis, this is the degradation multiplication factor. So, take an example. We go from a temperature of 50 to 60 degrees Celsius. We see that the degradation multiplication factor will be doubled. So what does it mean for a component? Simply that you will divide by 2 the lifespan of your component. This is a lot. Each 10 degree, you will divide by 2 the lifespan of your component. And this is even more true for LEDs, sensitive component like LEDs, or ICs, especially ICs that eats a lot. This would be really a problem for high frequency traces, because we will not go into detail, but this must be precise dimensions. And if you change a little bit the dimension, then you will have an impedance mismatch that will create trouble in your signal integrity. Another concrete example is the thermal expansion. Here you've got the thermal expansion of copper, which is 16.5 micrometer per meter per Kelvin. This is more or less the same than FR4 in that direction, but that's not the case at all in that direction. So if you heat too much your PCB, you will have different way to expand your material. And so at the end, if it's too much calories, temperature, then you could have a delamination of your traces, your copper traces. And of course, that's an issue for your everything, signal integrity, power, and everything. Now we will talk about a little bit standards. So don't run, it will last 4 or 5 minutes only. And after that, we will go into more concrete topic. There is mainly 2 big standards that give you the opportunity to design your traces. First, this is the IPC 2152, and the name of this is Standard for Determining Current Carrying Capacity in PCB. So the title exactly says that this is the right standards for current designing. So here you can see that the abacus are floated. This is for copyright reason. We have to buy it. Well, of course, we bought it. Würth Elektronik company bought the standards, but I'm not able to show it clearly because you have to pay for that. That's not really expensive, and that's really easy to use. So you will find this standard a lot of abacus, for example, and the current limit is roughly 20 amps. So most of the application. We'll take the example of 10 amps. We want to design a trace 10 amp 40 at a temperature rise around 45 Kelvin, so 45 Kelvin above the ambient temperature. The current is here, 10 amp, and then here you see lines that defines from 1 to 100 degrees Celsius. You cross the 45 Kelvin here, and then that gives you 0.15 square millimeter, which is the cross-section that you want to reach for your trace. Imagine that you would like to have a 70 micrometer of thickness for your traces. Then 0.15 square millimeter, you cross the line of 70 micrometer. Then you have a width of 2 millimeters. That's quite easy. But there is another way, another standard that is called, probably most of you know that standard IPC 2221, because there is a lot of design details for the PCB. That's called generic standard on PCB. You can find current, material, creepage, clearance, a lot of different things. And in this, you are able to design also the current, the cross-section of your trace. This given by this strange formula. A is the cross-section in square mils, so this is imperial. Well, that's IPC coming from United States, so that's why this is in square mils. But of course, you can easily translate it into a square millimeter. It depends, of course, on your current. It depends, of course, of the delta T that you want to reach. And from this factor K, which is given by if it's an outer layer like this one or an inner layer like this one. In a second, I will show you what is the impact. But what is the big interest of that formula is that there is no current limit. You can go up to 100, 200, 500 amp. For example, if you use or red tube that you can go up to really high current, then you can use this formula. Concerning outer and inner layer, I did this small curve. There is a trace cross-section, x-axis, y-axis, the current. If you use the formula for outer layer, then for 10 amp, you will have a 0.13 square millimeter, 0.4. Then, if you put your current inside of the PCB, then you will have to design a higher cross-section for the same current. Obviously, if you're outer layer, then you will have more thermal exchange with the environment and, of course, with the air through convection and radiation. And if you compare these two standards, then I did that with a curve, always trace cross-section, current here, and that's the way how you can design the delta T for a trace. Imagine 20 Kelvin, IPC 2221, and the same delta T for the trace IPC 2152. Then for 10 amp, you will have a smaller cross-section for IPC 2221 than for the other standards. The same current and a smaller cross-section means that you will have more delta T. So very probably we can feel that one of these will be better, or at least IPC 2152 should eat less than IPC 2221. So how can we know? We just have to test it. So that's what I did. I did a small PCB with different cross-section for 10, 20, 30, 45, and 60 Kelvin. So that's the design of these traces. And then you put the same amount on 30 currents. You do the measurement of what is the real delta T on your PCB. That is the results here in gray. That's the delta T trace design. So 10, 20, 30, 45, 60. And that's the blue. That's the reality, the delta T PCB measurement. So first, what can you see is that this is not so bad. This is really close to what is planned by the IPC 2152. So this IPC gives predictable values. One thing more than you can see is that the connector is always cooler than the trace. What does it mean? It means that the connector is designed to heat not so much to limit the temperature rise, always. So the connector in that case will play the role of trace cooler, and you will see that wire does the same. We say that for the IPC 2221, it gives smaller cross-section. That is what we will see here, because this is exactly the same example. I did a PCB 32 amps, 57 amp. This is a trace designed for 45 Kelvin, 60 Kelvin, 45, 60 Kelvin. And as you can see, the gray is the delta T trace design. This is really lower. So IPC 2221 is hotter than expected. This is a little bit like Würth Elektronik. This is more than you expect, but for this, that's something that you don't want. So now that's the end of the standards. Now we will see something maybe a little bit more concrete. How to do better. We know now that we don't have to go too high in temperature. We know that how to design a trace. And now we will see how easily you can decrease the temperature on your PCB. A small reminder, a copper has a thermal conductivity of 400 watts per meter per Kelvin, which is really good. But the FR4 conduct temperature very, very bad. This is very bad. So what does it mean? It means that the temperature will be stopped by FR4 and very good conduct by copper. Copper means trace, ground layer, means connector, and also wires that goes inside of the connector. And just as for information, basic plastic is a very bad, has a very bad thermal conductivity. Also, water, steel, air, obviously, steel, brass, and aluminum. As you can see, thermal conductivity works a little bit the same way as electrical conductivity. Well, the more you conduct electricity, the more you will conduct. So how can we know? How can we make sure that the tips are working? So I did a small PCB like this one. This is always the same terminal, always the same. Well, apart from this one, which are SMT, but we will not talk about that today. This is too short, 30 minutes. They are all in series, so the wires are always 16 AWG. This is designed for 10 amp. The trays are all designed for 10 10 amp, exactly the same way with IPC2152. And the widths, the cross-section are always the same. For example, this one has a width of 2 millimeter, this one 1 millimeter, but you've got one other millimeter on the bottom layer, okay? And the length of the wire is around 15 centimeter. Now I have a small video. Have to go back to. No, that's not working. How can I launch my video? I'm not able to launch the video. Unfortunately, that's the shame, because I'm quite proud of my video because of the option. Sorry, I insist a little bit. So that's a video that you 11 minutes, because of course the temperature is long to increase. And this is something that you can see. This is always the same current, always the same traces, always the same wire, the same connectors. And you can obviously see that the temperature is definitely not the same. This is what we will study right now. So I will come back to trace delta T 5 Kelvin. In the reality, that's 13 in the reality, 9 Kelvin. So that's confirmed that the IPC2152 gives predictable values. Okay, but now we have two traces. And of course, if you put two traces close together, then that's the same. If you put two radiators in the same room, then you will heat more. Then we go from 39 Kelvin to 57 Kelvin. Okay, so that's a little bit more. And if you have one trace 2 millimeters on the top side, or here 1 millimeter on the top layer and 1 millimeter on the bottom layer, then you will heat exactly the same. See, 30 Kelvin connectors is always less. That's too much. Now we want to do one additional thing, which is a thing that is quite interesting. This is a picture of the cable. You see that the connector and also the cable, because the cable are done in copper, then will pull out the calories out of the connector and out of the PCB. That's really important to know. And as you can see, after a while, the wire is cold. Then no need to have a very long cable to pull out the calories outside of the PCB. Above 10, 15 centimeters, this is useless. But if you cut your wires at 5 centimeters, then it will not be long enough to cool down your PCB. So be careful. Normally, the minimum is 10, 15 centimeters. How to cool down your PCB? Then we said that the copper is a very good thermal dissipator. Then we will heat a top and bottom ground layer. So we'll see what is the impact. The impact is very big. The ground layer cool down your PCB of minus 20 Kelvin in that case, of course. And you will see this interesting picture is that this is the limit of the ground layer. And what you see here is that this dissipates a lot the temperature, but when you reach the FR4, then the FR4 is cold. And what does it mean? It means that you have no temperature dissipation anymore. So that really confirms that the copper has a very good thermal conductivity, but FR4 not. One other tip is separate your traces as most as possible. So in this example, we have two traces on the top layer and two traces on the bottom layer. They are not exactly at the same place. In that case, this is only minus 2. In that case, but I have other examples where this is very interesting. So in that example, minus 2 Kelvin is not so much, but as much as you can separate the power traces so they will be able to cool down better and to dissipate calories better. Another thing is that you could simply, this is very simple tool, is to add tin on your trace. Then you just have to remove the resin of your trace when you design your PCB, and then, or you use the wave soldering, and then it will naturally be done if it's on the bottom layer. Or if you use a reflow, then you put tin here, paste, and then it will be soldered during the reflow process. One thing that some people does not know is that the tin conductivity is not good. 14% only of the copper. So it could be better. This is a metal, but it conducts electricity, as we can say, not so good or quite bad. But the thickness, of course, of the tin is really higher than the simple 70 micrometer of the trace. So what is the impact? The impact is big, minus 17 Kelvin for your trace for the same current, same connectors, etc., etc. Just watch the time. Yeah, so we are on time. So another tip is increase the ground layer. Of course, I said that with the FR4, thermal dissipation stops. So why do not increase the ground layer? Of course, you will say, I don't have space. And I agree, but what is the limit of increasing the ground layer? Not so much, minus 5 Kelvin. And why not so much in that example? This is because, as you can see on the picture, the limit of thermal dissipation is around 1 centimeter. And after that, this is blue. Blue means cold, means that you have no thermal dissipation anymore. So no use to have a PCB of 1 kilometer long. It will be useless. But the bigger is the ground layer, the best it is, always. But there is one way to increase the thermal dissipation with a big ground layer or with a metal box around. This is thermal management interface that we have in our catalog, and in that case, this is a graphite sheet. If you remember, I said that the copper thermal conductivity is 400 watt per meter per Kelvin. This is very good, but graphite sheet is 1,800. This is really, really higher. So it will take the temperature and spread it in all directions. So it will increase the effect of the copper ground layer. The impact is huge also, minus 10 Kelvin if you use thermal management interface. Now, you saw easy tips to decrease your temperature. Is it applicable for the LEDs? On the same PCB, I put LEDs in different configuration. So this is power LEDs. The dissipated power is 2.5 watts. This is a lot for a really small component. And the maximum current is 0.7 amp. And I can tell you that this is really powerful LEDs because you don't have to watch that with your simple eyes. Otherwise, you will see white color for a couple of hours. So this is a little bit dangerous. So this is really power LEDs. The maximum temperature is 125 degrees Celsius. So what are these configurations? First is that you have no ground layer, no top, no bottom ground layer. Second configuration, top layer. Third configuration, top and ground layer. And you can bet the best configuration is ground, top layer, top, ground layer, and thermal via in between. I told you that the thermal conductivity between that face and that face, even if the PCB is really small, like for example 1.6 millimeter, is really bad. So the thermal expansion will be stopped here. And if you use copper vias between the two layers, then that will take the calories and bring them in the bottom, and the bottom will spread the calories everywhere. So this is how I did, and mainly you have to do that on the bottom of the LEDs. Now, the test. So here is a picture of the test. You see the lights of the 4 LEDs are exactly the same. This is a thermal camera, and this is what sees the camera, the thermal camera. This is an infrared camera that has no link with the wavelength of this LED. So what you see with the thermal camera is unique, has no influence with the brightness of the LEDs. As you can see, with only 0.3 amp, that's the maximum is 0.7, then you reach a very big temperature, 109 degrees Celsius. And the 3 others are, let's say, quite cold. At 0.4, the LED passed. And I mean, this really passed because I did it and poof, I saw a big brightness, and that was all. So you can not even use at half power and it blow up. Now we want to use at full power or LEDs, so 0.7 amp. This one with the top copper layer, ground layer, went up to 95 degrees, 2 ground layers, 85, and of course the best one is 33 degrees Celsius only. So we are going from something that we are not able to see because this is too high and it destroyed completely the LED, to something that is acceptable, 73 amp. And remember that each time that you decrease the temperature of 10 degrees Celsius, then you double the lifespan of your component, especially that's true for a LED. Now you understood what happens on this video, and you know what means this picture also. So, conclusion. Here we learned that 10 degrees Celsius lower, double the lifespan. Of course, if possible, oversize your traces, that's always the best, but sometimes you don't have space enough to do it. IPC 2152 design fits better to the reality than IPC 2221. I don't know how you're doing your traces usually, but IPC 2221 is usable for high current. Easy tips to decrease temperature that we saw today: add maximum ground layer, use thermal vias if possible, misalign power traces or separate them, use trace tint if it's possible for you. We didn't saw a test on that, but vertical, if you are able to put PCB on vertical position, that's always better because of the air movement. It will create a natural air movement that will cool down also your PCB on a horizontal way. Well, you don't have a 50 degree of difference, but that's always better in a vertical way. And of course, if you have a problem, that's really easy to use thermal management. Well, we have a lot of products in the catalog, but well, that's not really the topic to explain all of our products on thermal management today, but that will be another topic in another time. Last slide. Temperature is really easy to understand. Okay, we know if we touch something that is hot, then we remove the end. Everybody knows that. If you see a temperature picture with a thermal camera, red is hot, gray is not hot, or blue is not hot. Okay, this is really easy to understand. But this is very complicated in the reality and very hard to guess before what will be your temperature in the real life. So, or you simulate it with ANSYS, with something like that, or you should do a prototype. If you have a doubt, you should do a prototype to check if the temperature is really what you think.
To download the slides from today's presentation, simply click the link in the description or visit Würth Electronic Video Center at www.we-online.com/webinars. While there, you can also check out the entire lineup of heat management components available at www.we-online.com. We understand that some videos and images are not available on all streaming networks, so to replay the entire podcast with video, simply visit our website at www.we-online.com/podcast or check out the Würth Electronic YouTube page. You're listening to Würth Elektronik's What's Up radio podcast, where each week we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists. We're going to shine a light on interesting topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.